We'll finish up this set of videos going over how logarithmic properties and using a specific property of the logarithm is going to help us evaluate limits when we get an indeterminate form that is one of those exponential indeterminate forms that we really haven't learned how to deal with yet. So remember, anytime we have a limit, the very first thing that we're going to do is we're going to do the substitution theorem. So I'm just going to plug 0 in here for x. So I have 0 plus 1. Cotangent is the cosine over the sine. So what we have here is we have 1 to infinity. The cosine of 0 is 1. The sine of 0 is 0. In the context of the limit, this is 1 over tiny. And what's 1 over tiny? In the context of a limit, that's huge. So this is one of those indeterminate forms that we said we would revisit whenever we went through the indeterminate forms and L'Hopital's rule. It is an indeterminate form that shows up a lot when we have a variable base raised to a variable exponent. Everything we've done before has been some real number raised to a variable or some variable raised to a real number. Here's an exponential function. Here's a power function. This is neither. It's not exponential, nor is it power. So we have to determine how we're going to deal with it. So anytime we see a variable base raised to a variable exponent, think of introducing the natural log. And here's how we're going to do this. In this example, we're literally going to bring this function outside of the limit. See how I've dropped the limit notation and now I have defined the function to be y equals the quantity x plus 1 raised to the cotangent of x. And the reason I've done that is because I want to change the way this function looks without changing its value, and I've got to keep in mind that I am manipulating it, so once I manipulate it and stick it back in the limit, I've got to be careful how I finish up that limit work. So let's just work through this example. You'll get an idea of how it's done. I want to introduce natural log to both sides of this equation. It's perfectly legal as long as I introduce whatever mathematics I'm manipulating, whatever I'm doing on one side of the equal sign. As long as I do the same thing on the other side of the equal sign, I still get equals. Remember the power of that symbol. Why do I want to pull natural log? It looks like this is, this is bad enough. That looks much more complicated. Well, remember that rule that says the natural log of r to the n can be rewritten as n times the natural log of r. So I get to bring something that has maybe a variable base and a variable exponent, and I get to turn it into a product. I like a variable expression times a variable expression much better than I do variable raised to a variable. So now the natural log of y, if I use that logarithmic property, is the cotangent of x times the natural log of the quantity x plus 1. Now, I've changed the way it looks. I haven't changed its value. I've just changed the way it looks. Let's take it back over here and put it back inside the limit and see what we get. Now, cotangent is the cosine of x over the sine of x. So I'm going to write it that way. When tangent or cotangent shows up inside of a limit, sometimes it's easier to put it in terms of cosine and sine. And now the numerator is still times the natural log of the quantity x plus 1. So the cosine of 0, now I'm going to do the substitution theorem. The cosine of 0 is 1. The natural log of the quantity 0 plus 1, or the natural log of 1, is 0. So my numerator is 0. The sine of 0 is 0. And look what I did. I went from an indeterminate form that I can't do anything with to an indeterminate form where I can use L'Hopital's. So L'Hopital's says now that I have 0 over 0, I can take the derivative of the top, which is a product rule, 1 d2, that's 1 over x plus 1, right? Times the derivative of what's inside is just going to be times 1, so I'm not going to write that. So 1d2 plus 2 d1, and the derivative of cosine is negative sine of x. And all of that over the derivative of the sine of x. So that's positive cosine of x. So now let's do this again. We have, I'm going to plug in 0. The cosine of 0 is 1. 1 over 0 plus 1 is 1, plus the natural log of 0 plus 1 is the natural log of 0, so that's 0, and minus sine of 0, which is 0, and all over the cosine of 0, which is 1. And look, just in one step, one iteration of L'Hopital's rule, the outputs of this function, are headed toward 1. Now, I want you to notice something. We're not done yet. I want you to notice that this is not the limit. This does not equal the limit as x approaches 0 from the right of x plus 1 to the cotangent of x. What 1 is it is the limit of the natural log of that. So what I need to do is I need to realize I am taking the limit as x approaches 0 from the right of the natural log of that function y, and I found that to be 1. But I want the limit of y, not the natural log of y. So how do I get back to just y? How do I undo the natural log operation? Well, I undo that by bringing e to the party. So the limit as x approaches 0 from the right of e to the natural log of y has to equal e to the 1. So the limit of the original function, the limit as x approaches 0 from the right, wow, come on mouth, of my original function, where I got that indeterminate form I didn't know what to do with, those outputs are actually going to e. Now I'm done. There's my final answer. So introducing logarithms, especially when we have a variable base to a variable exponent, introducing natural log is going to help us actually be able to evaluate that limit, but we have to remember that final step is that we have to take natural log back home. We have to bring e to this party. All right, there's the fourth and final video for this lesson. I know it was a lot of information, but you were going to get it either in this lesson or in a later lesson, so we might as well get it now. Come to class next time and we'll do some homework problems.